So we've covered the key activities in systems engineering. We've looked at the process, its characteristics, the roles, and how everything comes together. But before we enter the modeling world, we need to talk about optimization and trade-offs. Systems engineering isn't about finding the perfect solution, it's about finding a solution that balances the needs of the project, the engineering, and the stakeholders. These needs can often be in conflict with each other, and ignoring any one of them can throw the whole project off track. If we focus too much on the technical side, we might exceed the budget or miss key deadlines. If we ignore the customers, we won't build the right thing. If we don't listen to specialists, we won't even have a product to sell. We are after a suitable solution, one that works, is feasible, and meets the goals without causing a major disruption to the project. Let's take an example from the railway industry. Imagine you're tasked with designing a new fleet of trains for a country that's looking to be more sustainable. You have different options: hydrogen, electric, or maybe a hybrid between the two. Now, all of them sound like great choices, right? But each of these options has its own set of trade-offs. There's a huge decision tree here with lots of branches. On one hand, hydrogen trains can use existing infrastructure, even unelectrified tracks, meaning you can quickly deploy them in remote areas. But the infrastructure for hydrogen production and transportation is not yet mature. On the other hand, electric trains are typically more energy efficient, and we have decades of experience on the technology. It is field proven, but they rely on access to extensive infrastructure, like overhead lines or rail electrification, which could be a challenge for some routes. And the hybrid solution? Well, it balances between the two, but might not be as optimized on either end of the spectrum. This is where trade studies come in. Trade studies help us compare these options based on a set of criteria: performance, cost, environmental impact, and most importantly, the project's goals. It's about weighing the pros and cons of each option and finding the one that balances those factors the best. The decision isn't easy, but it's necessary. We're optimizing the design to meet the needs of the project, but we're not necessarily looking for the perfect design. A perfect design might be too expensive or too complex to implement, and that could set the project back by months or even years. Instead, we focus on finding a solution that's suitable and will work in the real world. And here's where it gets tricky. Every decision you make creates a decision tree. Let's take that railway example again. Do we go with hydrogen, electric, or hybrid? If you choose hydrogen, how about the traction motor power? Do you use fuel cells or a hydrogen internal combustion engine? Each decision leads to different branches: cost, performance, environmental impact, and infrastructure requirements. We could follow each branch to its end and figure out every possible outcome, but the sheer number of potential combinations is overwhelming. Now, most of the solutions are not viable to the projects for various reasons, and one of them is the best we could achieve. But there are others which, even if not the best, will satisfy the project. The problem is, we don't have the luxury of infinite time or resources to explore every option. So what do? Well, instead of trying to find the perfect solution, we aim to make good decisions based on the information we have. We use domain expertise to guide us. For example, if your team has more experience with electric trains, you might lean towards that option, but we still need to keep an open mind. Systems engineering teaches us to be cautious of biases. Just because something has been done before doesn't mean it's the right solution for this project. We need to explore new possibilities without falling into the trap of sticking to what's familiar. But maybe fully electric is not adapted because there's too much infrastructure cost. So you explore train with hydrogen combustion engines, but realize that it's not going to cut it and lean toward a hybrid solution. As we move forward, we refine the options and make decisions. But remember, systems engineering is an iterative and recursive process, so those trades happen in every activity, whether you're in the conceptual design or detailed design. Every time we make a decision, we go back and check it. Does this choice still work? Does it align with our goals? Can we make further improvements? This helps ensure that we don't backtrack too far down the wrong path. Trade-offs are not only about selecting a technology, like in our example, it's more general than that. Even at the very beginning of a project, during the concept definition activities, trade-offs are important. For example, let's say you want to send humans to the moon to do experiments. How do you do that? Well, you could do an Apollo-style mission where you take everything you need in one go, or you can split the mission. Send all necessary utilities, equipments, and rovers first, assemble the lander in orbit on a space station, then send humans. This is what NASA's Artemis program aims to do. Now both have pros and cons, and there were probably other concepts to solve this problem, and NASA made its choice. In the end, systems engineering is an optimization problem. It helps to find an efficient solution considering everyone involved in a project.